наверное.
Видите, даже дамы не возражают.
По-русски или по-английски? Закладывать.
А какие у нас случаи? Да давайте по-английски, что там?
По-английски. Окей. Окей. So,
Александр Яковлевич, вы представите докладчика или мне?
Давайте вы, Алеша,
Yeah.
конечно.
So today our speaker is Vladimir Troitsky from University of Alberta, and the title of his talk is Vector Lattice Generated by Finite-Rank Operators with Applications to Tensor Products of Banach Lattices. Please.
okay, so before I start, I would like to thank Timur, who is here, who helped me with this project a lot. We discussed these things with him for a long time. And also some of this result that I will present actually were known to Arendt. There is a paper by Arendt in I think in the 70s, but he used completely different methods. So my method is more or less elementary and direct. So it's a little, I would say, little nice observation. So let me first introduce the terminology, and some of this terminology you probably have seen, but maybe refresh that by ordered vector space, an ordered vector space, I mean just a vector space which is equipped with a partial order such that the two structures are compatible in the natural way that if x is less than or equal than y, then I can add the same vector to the both sides. X plus z is less than or equal than y plus z. And I also can multiply both sides by the same non-negative number. Lambda x is less than or equal than lambda y, where lambda is a non-negative number. I will also assume, through this talk, I will also assume Archimedean property. But for most cases, it will be automatic. So I don't, in most cases, for Banach lattices, it will be automatic, so I don't have to assume it. It's already there. Now there is standard notation by x plus. If x is an ordered vector space, then x plus is the positive cone, so the set of all positive vectors. Say all x in x, such that x is greater than or equal to 0. Now a vector lattice is a stronger condition. So a vector lattice is an ordered vector space plus lattice. And this means that for every x and y, the supremum of xy exists, which we denote x sub y, this symbol. And this also implies that the infimum exists. This follows automatically. And now if we have a vector lattice, again, we use the standard notation. By the modulus of x, we mean x sub negative x. So modulus is an operation from x to x. So for every vector in x, we can consider its modulus. And finally, a Banach lattice is a vector lattice plus a Banach space such that the norm is monotone and the norm of the modulus is the same as the norm of the vector itself. Okay, so these are all the axioms. And well, as I kind of as justification that most classical Banach spaces happen to be Banach lattices. So this is a natural, these conditions are natural. Now a few words about operators. So let's say if we have an operator. So let an operator between let's see if X and Y are ordered vector spaces. Okay, let's say vector lattices. It's easier for us that if X and Y are vector lattices, and let's say T from X to Y is a positive operator, is a linear operator. Linear operator. We say that T is a lattice homomorphism. If it preserves lattice operations. So T of X sub Y equals T of X sub T of Y for every X and Y. And well, because lattice operations, supremum and infimum modulus, they can be expressed with each other. Actually, it's enough that T preserves any one of them. So let's say if T preserves the modulus, it's already enough that it's to conclude that it's a lattice homomorphism. But a lattice homomorphism is quite a strong condition. A much weaker condition is to say that T is positive. So T is positive if it maps the positive cone of X into the positive cone of Y. So it sends positive vectors to positive vectors. And there are positive operators are quite common in applications. They appear naturally. So there are a lot of operations that are a lot of operators that are positive. In particular, every lattice homomorphism is positive. This is an easy exercise. So lattice homomorphism is a rather strong condition. And we denote all positive operators from X to Y by LXY plus. Now we also say that T is regular. T is regular if T is, well, there are several equivalent definitions. The one that will be most convenient for me now is that plus minus T is dominated by a positive operator. Or equivalently, if T can be written as a difference of two positive operators. And I will write L sub R xy for all regular operators. Actually, maybe it would be more convenient to use straight L. And the reason for this is that in a Banach lattice case, if X and Y are Banach lattices, then every regular operator is automatically norm bounded. So LR of XY is actually a subspace of the space of all bounded linear operators. But in general, we can say that LR is just the span of all positive operators. Because it's differences of positive operators. Now, for a regular operator in the Banach lattice case, if now let's stick to the Banach lattice case. So for a regular operator, we can define its regular norm. So the regular norm of T is the infimum of the norm of S, where S is a positive operator which dominates T. And generally, the regular norm of T is greater than or equal than the operator norm. So this is not equal to the operator norm. And there is a fact, which is not very difficult, that LR is a Banach lattice, is a Banach space. under the regular norm. So in my talk, whenever I mention LR, I will always mean LR with the regular norm. Okay, so up to now, everything seems to be fine, but now let me tell you some bad news that, well, the category of vector lattices and Banach lattices, there is one big issue that spaces of operators are not vector lattices. So if you consider, again, even if in the case of Banach lattices, unfortunately, LR, well, neither the space of all operators, nor the space, if you consider the space of all operators or the space of regular operators, these are definitely ordered vector spaces. But in general, not lattices. So for some operators, we can still say that the modulus of t, which we can define it as the supremum of t and negative t, and this may exist for some operators. So we have like partially defined. We have partially defined lattice operations, but there are operators which don't have modulus. And this causes a lot of troubles. This causes a lot of difficulties, but this is also a source of many interesting results. That this category is not closed under going to spaces of operators. In particular, if we have a regular operator, if T is a regular operator, then it's easy to see that the adjoint, well, T is just the difference. Let's say we can write T as difference of two positive operators. And then T star would be the difference of T1 star minus T2 star. So which means that T star is also regular. But the regular norm of T star, in general, we can say that it's less than or equal than the regular norm of T. And generally, we don't have equality. So in other words, the map, yeah. So the adjoint map is not an isometry. The adjoint map is an isometry with respect to the operator norm, but not with respect to the regular norm. And similarly, if we consider this diagram, so we have Tx from x to y, and now we can compose it with the canonical inclusion of y into the second dual. Then this operator Jt, this will be a regular operator from x to y double star. But the norm of it, the regular norm, generally is not the same. We only can say that the regular norm is less than or equal than the regular norm of T, but generally we don't have equalities. There is one special case when things are nicer. If Y is a dual space, so if we consider the space LR of X to Y star, in this case, operators do form a lattice. So this is a lattice. Moreover, it's a Banach lattice under the regular norm. But even in this case, these two inequalities are still inequalities. So these two inequalities, they don't become equalities even in this nice case. Now, one more piece of background is this Risch-Kantorovich theorem, which is a very useful tool in this area. So Risch-Kantorovich theorem says that suppose we have an operator, so let T be, it's actually, it could be, let's say X and Y are vector space, lattices. For Risch-Kantorovich, it's enough that X and Y are vector lattices, and T is a linear operator from X to Y. Okay, we can restrict to regular operators, but suppose that that for every x, the following set has supremum. So if we take supremum of the modulus of t y over all y which are dominated by x. If this exists, then we know that the modulus of t exists. And moreover, the modulus of t is given by this very formula. So the modulus of t of x is actually equal to the supremum. For every x, sorry, I forgot that x must be a positive factor, for every positive x. Okay. So this formula is called the Risch-Kantorovich formula, and well, this is a formula for supremum, but there are similar formulas for this is a formula for the modulus, but there are similar formulas for supremum, for infimum. In particular, for supremum, we can actually do it for more than one operator. We can say that the supremum of several operators, let's say we have operators from 1 to n, the supremum of several operators at x would be, we can compute this as the supremum of the sum as I goes from 1 to n of ti xi, where xi's are all possible decompositions of x into positive vectors. So x1, xi's are all positive, and x is the sum of xi's. So in particular, if this formula is always, if this supremum exists, then our operators actually form a lattice. Okay, so these were very classical results. Now let me mention something which is not quite classical, but which is actually very easy. So let me say fact 1. Suppose that X is just an ordered vector space. Okay, so I don't even assume that X is a lattice. And Y is a subspace. Suppose that Y is a subspace. But suppose that Y has this very strong property that for every finite subset of Y, there is a supremum. Suppose that this supremum exists in X. Okay, so we're not saying that it's in Y, this supremum exists in X. So we can now define this set. So we write Y, this check, will be the set of all supremo finite subsets of Y. So this is the set of all vectors in X, which are formed as supremo of finite subsets of Y. So now this set is defined. Now I claim that this set, if I take Y check minus itself, this is a vector lattice. Okay, so in such a case, this subspace, even though this subspace by itself is not a vector lattice, but it generates a vector lattice inside X. So we have a vector lattice inside an ordered vector space. So this is I will skip the proof, but the proof is really a simple exercise. It's a 4-line exercise. Now fact 2. Again, interesting fact. It's interesting by itself, and this goes back to Krengel. He proved it under some additional assumptions. So let X be a Banach lattice. So X is a Banach lattice. Suppose that Y is a finite dimensional subspace. And suppose that we have a set which is inside this subspace and which is norm bounded. So again, we have a subset of a Banach lattice which is contained in a finite dimensional subspace and which is norm bounded. Then we claim that this set of all upper bounds, now it's definitely defined because X is a Banach lattice. We can take up all suprema. So every finite set has a supremum. So now this set is well defined. Moreover, this set, okay, this is not really a part. So this set is defined. And just by construction, this set is directed upwards. So we can view it as an increase in net. Okay. But this doesn't really use any assumptions. But what we really, when we really use assumption, we claim that this net actually is convergent. Is convergent in norm. And the limit of this net is the same as the supremum of this net, which is the supremum of the original set. In particular, the supremum always exists. Okay, now next, let's say x, from now on, x and y will be Banach lattices. And by f of xy, I mean all finite rank operators. All operators of finite rank all bounded finite rank operators. Well, it's easy to see that this is actually, so this is contained, so finite rank operators are regular, because rank 1 operators are regular. So my goal is to convince you that while general operators may behave badly, finite rank operators behave very nicely with respect to these lattice properties. So the first fact, interesting fact, so let me call it fact 3. And well, for fact 2, I'm skipping the proof, but the proof of fact 2, the shortest proof is by reducing things to spaces of continuous functions and using Arcella-Ascoli theorem. It's kind of, and the proof is quite elegant. It's short and elegant proof. Okay, so now fact 3. Under these assumptions above, for every, if I have finitely many operators, finite rank operators, their supremum exists. So here, let me just sketch the proof. Because now we have all the machinery. We go back to the Risch-Kantorovich. You see, Risch-Kantorovich gives me this formula. So this is the formula for the supremum. So I only need to prove that this supremum exists. Okay, so what I need to show? I need to show that this supremum exists. But so let me write this as supremum of a set AX, where this is the set AX. But what is this set? So this set AX, it is contained in the ranges of, in the sum of the ranges. So this set is contained in the sum of the ranges of operators, which is a finite dimensional subspace. So this, let me write it here. So AX, this set AX, is contained in the sum of the ranges or union of the ranges of finite rank operators. So this set is contained in a finite dimensional subspace. And again, from this definition, it's easy to verify that it's non-bounded. Just the way it's defined, these expressions, they're all bounded because everything is dominated by X. Everything is controlled by X. So this set is contained. So this set satisfies the assumptions of fact 2. So by fact 2, the supremum of this set exists. And that's all we need. So supremum AX of supremum AX exists by fact 2. So that's really all. But now once we have this fact 3, now we can combine fact 3 with fact 1. So now we can think of it this way. So we have f of xy is a subspace of LR of xy. And we know that we have that for every finite set in it, the supremum exists. So now let's go back and revisit fact 1. Yeah, here is fact 1. So it says that whenever we have an ordered vector space, and inside we have a subspace such that every finite set has supremum, then we can actually get a vector lattice out of it. We're exactly in this situation. So this means that if we take this check minus itself, now this is a vector lattice in LR of xy. So let me give it a name. Let me call it G. Okay. So I just denote this by G. So even though LRXY is not a lattice, but inside it we have a like finite rank operators generate a lattice inside something which is not a lattice. But now the elements of this space themselves may not be finite rank. So actually this G is a bigger space. So it does contain operators which are not finite rank. Well, we'll see later that they all have to be they all have to be compact. So they are compact, but they don't have to be finite rank. With some more work, which I will skip because my time is limited, I can say that the maps, okay, so first the map, the adjoint map, T goes to T star. When we restrict it to this space, so we already know that in general this map is not very nice. But on this space, it's a lattice isometry. So what I mean by this, well, I mean by this that first the modulus, it respects lattice operations, and the regular norm of T star equals the regular norm of T. So it's an isometry with respect to the regular norm. And similarly, the map that sends T into this JT, so now it's a map from L of xy to L of xy star. Again, when we restricted it to this G of xy, then again this map is a lattice isometry. Okay. But now G of xy by itself is just a vector lattice. What is interesting, it naturally suggests that we can consider the closure of it, because it sits inside of a Banach space. So we consider the closure G of xy in the regular norm. Then this has to be a Banach lattice. Because it's a closure of a vector lattice under a lattice norm. And now if we go back, these two maps, the adjoint map and the J map, we can now extend them to this closure. So they are lattice isometries on this closure as well. Okay, so this was kind of the first part of my talk, but I promised applications to tensor products. So now let me move on to tensor products. And let me go over some facts. So first fact that I want to recall is how do we construct the injective tensor product between Banach spaces? So forget about lattices for a moment. Let's go back to classical Banach spaces. So then we can embed the algebraic tensor product. We can embed it into L of x star y by, we just think of an elementary tensor. If we take an elementary tensor, we can interpret it as an operator on x from x star to y, which acts in the only possible way. So we can treat elementary tensors as operators, and then we can treat all elements of the algebraic tensor products as operators. And now we just define the injective tensor product as the closure of this algebraic tensor product in L of x star y with respect to the operator norm. Observe also, so now we have this x algebraic tensor product sits in the x injective tensor product. This sits inside L of x star y, and this we can isometrically embed into L of x star y double star, because for operator norm this last inclusion is an isometry. So we can think of the injective tensor product sitting either in this space or in this space. It doesn't matter. So for all practical purposes, we can think of it. So we can think of injective tensor product as a subset of L of x star y double star, and in this case the identification will be slightly different. Now this will be elementary tensor acts in this way, where y check is, oops, something. Okay, something stopped working. Just a second, I will try to reset this machine. Okay, it's working. So y check, this is just j of y. Okay. So this is the first fact that I wanted to remind you. And the second fact is the construction of Fremlin tensor product. So let x and y be two vector lattices, well, Archimedean. Then Fremlin proved that we can construct a space which he calls, well, we will call it Fremlin tensor product of x and y, or vector lattice tensor product, which has this universal property that if you have it is defined by the following universal property, that if you have a bilinear map, bilinear and bihomomorphism. So bihomomorphism, it means that phi of xy, the modulus of phi of xy is phi of the modulus of x, modulus of y. So it's like homomorphism, but with respect to lattice structure. And now x, y sits inside, we have this embedding into this Fremlin tensor product. Then we can, and z is any vector lattice, so z is any vector lattice. Then we can extend this. There exists unique phi bar, which is a lattice homomorphism. So every lattice bimorphism lifts to a unique lattice homomorphism. So Fremlin proves that such a space exists, so we will use it. Also, we say that phi is bi-injective if whenever phi of xy equals 0, this implies x equals 0 or y equals 0. So it also follows from Fremlin's construction that this is equivalent that phi bar is injective. So phi is bi-injective precisely when phi bar is injective. And in particular, this Fremlin tensor product, it contains the algebraic tensor product. It contains it as a generating subspace. Meaning that the sublattice generated by the algebraic tensor product is the entire Fremlin tensor product. Now I need one more piece of notation. So by x plus tensor y plus, we mean the cone generated by the elementary tensors of positive elements. So this is all elements of the form xy, so finite sums of elementary tensors, where xi's are all positive in x, and yi's are positive in y. And observe that these elements will be positive in the positive cone. So this is contained in the positive cone of Fremlin's tensor product. But what is a bit surprising that actually we don't have, like, these are not all algebraic elements of the algebraic tensor product. So what we have is that generally we don't have this equality. We don't have this equality, but there are two important density results. One is due to Fremlin, which shows that the algebraic tensor product is kind of uniformly dense in the Fremlin tensor product in the following sense that so if we take an element in the Fremlin tensor product, then we can find a positive elementary tensor such that for every positive epsilon, we can approximate this A with an element of the algebraic tensor product up to this so we can control this by this rank 1 tensor. And the second fact, which is due to Fremlin Telegram, which says that even these two cones are not the same, they are very close to each other. Okay, so it says that if you have an element A in the algebraic tensor product, then A is positive with respect to Fremlin tensor product, if and only if we can find an elementary tensor such that A plus R, so every perturbation, this should be elementary tensor, every perturbation of A by this elementary tensor is in the small cone. For all positive R. This is quite a deep result, which requires some serious work. Okay, so now how we're going to apply this? So now let X and Y be Banach lattices. So I'm going to present a simple way to construct the injective tensor product of Banach lattices. The lattice injective tensor product. So it's denoted. It's not my invention. It existed a long time ago. There is a standard notation for it. This lattice injective tensor product. But the classical construction is quite heavy. I think what I can show now is a much more natural construction. So the construction goes this way. So we consider, just as in Banach space case, let's go back. In Banach space case, oh,
He's not satisfied with what he says. Ну, Володя, давай, просыпайся.
okay. Something,
Ну,
okay. I'm sorry, something failed, so I had to restart it. Can you hear me now?
yes.
Okay, so okay, I hope that let me restart the you would expect that by now this technology should work without interruption. Okay, so okay, so I can continue now. Let's hope it works now. Okay, so just as in case of Banach spaces, we embedded, remember that for Banach spaces, we embedded algebraic tensor product into L of x star y. And this we embedded, we had this sitting inside of x star y double star. Now we will do something similar. So we can say that we can define the map from x times y to L x star y double star just as we did before. So phi of x y applied to x star is just x star of x times y hat. But now in our new setting, now when x and y are Banach lattices, this map phi is bi-injective lattice bimorphism. Again, I will, because time is running out, I will leave this as an exercise, but this is a simple exercise. You just use Riesz-Kantorovich formula. Just expand, just write down the Riesz-Kantorovich formula for the modulus and everything works. So, but this means that by Fremlin's construction, we can now have phi bar from the Fremlin tensor product to LR of x star y double star, because here this y double star, because it's clear from the construction that we only get regular operators. So really there is no harm to put regular here. We only get regular operators. And now because the original map was bi-injective, now this is an injection, so we can actually think of the Fremlin tensor product sitting inside this space, sitting inside LR of x star y double star. So we can define the injective tensor product as the closure of the Fremlin tensor product viewed as a subspace here, so I can think of it as the range of phi under the regular norm. Now you say that, well, in the classical Banach space case, it doesn't matter here, we can use y or we can use y double star. Can we do the same with y double star replaced with y? Well, the problem is that, okay, we can still consider this map for y, defined in the, again, in the only natural way. The problem now is that this space, okay, LR, this is not a lattice. So we cannot, formally speaking, we cannot apply Freblin's construction. But we can fix this because, okay, this space is too big for us. We can replace it with a smaller space. We can actually think of phi of psi acting into this g of x star y. So now inside of this big space, which is not a lattice, inside of it we do have a lattice. So now we can use Fremlin. So now we can have psi prime, which now goes from Fremlin tensor product into g of x star y. And now this sits inside of a Banach space. So now we can take the closure. So the result is the same. The result is the same. So the closure will be the same because we already know that on this space on g of xy, the embedding, we can think of g of x star y as sitting inside LR of x star y double star, because we know that on this space, this map that sends t into jt is a lattice isometry. So we can use this space to construct our injective tensor product, or we can use this space to construct our injective Fremlin tensor product. It doesn't matter. We get the same result. And now using density, we can prove. Okay, so let me. Using density, we can prove that. Okay, so another fact that for an element in the Fremlin tensor product, we can prove that the lattice injective tensor norm of A is the infimum of the usual injective norms of C, where C belongs to the small cone. Sorry, and C dominates A. So now this becomes a corollary, and now this corollary, actually, this is in old literature, this is how this tensor product was defined. But for me, this is rather a corollary, and it follows from Fremlin's density results. Okay, so now consider the following case. So before we had everything in x star y, but now I want to go it kind of backwards. I will consider a map phi from x star times y to L of xy, again defined in the natural way. Okay. And again, I can actually view this as a phi from, because I only get finite rank operators, so I can actually think of it as a map into g of xy. So now this is a map into a vector lattice, and we can verify easily that this is a bi-injective bimorphism. Injective lattice bimorphism. So by Fremlin, we can extend it to the Fremlin tensor product. And now think of it this way. The range contains all finite rank operators, because they just come from the algebraic tensor product. Already the algebraic tensor product already gives you all the finite rank operators here. But now G of xy is a lattice generated by finite rank operators. So this means that, and the range of phi bar should be a lattice. So this means that phi bar is onto. But because we started with a bi-injective map, it's also one-to-one. So this tells me that the resulting map is actually a lattice isomorphism. So this gives us a description of G of xy. So G of xy as a lattice, it's lattice isomorphic to the Fremlin tensor product of x star and y. And then we can pass to closure. So if we pass to closures, we can say that the closure is lattice isometric to the lattice injective tensor product of x star and y. Okay, so now these two spaces, they kind of came up in a different ways, but they actually lattice isometric. They're lattice isometric. In particular, I can now use density results. So again, using density, Fremlin's density, I can say that the algebraic tensor product, which is nothing but f of xy, I can now sits is uniformly dense in this G of xy. So let me write this down formally. So for every, if I have T in G of xy, then I can find a finite rank operator such that for every epsilon, sorry, not just a finite, a rank 1 operator. There is a rank 1 operator. Rank 1 operator U, such that for every epsilon, I can find S in finite rank, a finite rank operator, such that the modulus of T minus S is less than or equal than epsilon times U. Okay, so every operator in the G space can be approximated by operators of finite rank with an epsilon where with this controlled by the single rank 1 operator U. In particular, this implies that the operator norm is dominated. I can just take the norms of both sides, the operator norms or the regular norms. So this means that f of xy is dense in any sense. It is dense in the operator norm and in the regular norm in G of xy. Which means that when we consider the closure, so the closure of G that we discussed it before, this space, it is actually the same as the closure of f of xy. So here we get a corollary which was known to Arendt, that the closure of f of xy is a Banach lattice. But now we get this corollary almost for free. Well, not for free. We use Fremlin's density. Arendt proved this using some special technique of tensor products, some M tensor products, which definitely I don't want to go into this now. And in particular, this implies that these maps, the adjoint map and the composition with J map are lattice isometries on this space. So now this space, this closure of G and closure of finite rank operators are the same. So this means that the adjoint map and the map, this map are lattice isometries on the closure of finite rank operators. And I think that's where I should stop. I think I'm running out of time, so this would be a good place to stop.
Thank you. By the way, if you need more time, you have half an hour, because usually the normal duration of talks is 1 hour and a half.
Oh, I didn't realize this. Okay, I could have proved, I could have shown some of the proofs then, because I skipped. Maybe I can, if I have a few more minutes, I will show you the proof of this fact too, because I think it's a nice proof by itself. Okay, I will take maybe not half an hour, but maybe 10 more minutes, if you don't mind. So let me recall this fact. I think I called it fact 2. That, let's say we have X a Banach lattice, Y a finite dimensional subspace, now A is a subset of Y, which is norm bounded. And then these were the assumptions, and the conclusion was that A check is a convergent net, and the limit is the supremum. Well, the last part is for free, so the difficulty is the convergence. Okay, so the proof here is an outline of the proof. So every finite dimensional subspace is contained in a principal ideal. So we can think of Y as a span of some vectors, say Y1, Yn. So now we define E to be the supremum of this. Okay, so this is a standard kind of, the beginning is totally standard in this area. So now we consider the ideal. So I sub E is the ideal generated by
Now
the ideal, order ideal of X generated by E. And there is a classical fact that due to Crane and Kakutani, that this space IE, it can be represented, okay, it has its own norm. Let me define its norm. So on IE, I can define a norm, a different norm, E norm. This is the infimum of all such lambdas. Well, we know that every element, if X is in IE, then X is dominated by some multiple of E. So I will take the least such lambda to be the norm. Infimum of lambda such that X is less than or equal than lambda E and lambda is positive. So now IE with this norm is itself a Banach lattice. And the classical Kakutani-Crane theorem says that it is isometrically isomorphic to some CK space. For some compact K. And now by the construction, by the way I constructed it, every element of this Y space is contained in IE. So I see that Y is contained in IE. So we can think of Y, we can identify Y as a finite dimensional subspace of CK. Now this, because Y is finite dimensional, on Y all the norms are equivalent. So on Y, the original norm of X is equivalent to this norm coming from CK. This E norm, which is nothing but the E norm. In particular, because A was norm bounded in X, it would still be norm bounded here. So A So now we have a subset of CK, which is norm bounded and is contained in finite dimensional subspace. So this means that A is relatively compact. And by Arcella-Ascoli, we means that it is equicontinuous. Because by Arcella-Ascoli, in CK spaces, equicontinuous precisely means norm bounded, and relatively compact precisely means equicontinuous and norm bounded. But now the key observation is that when we go to this, when we consider this a check all upper bounds, if you consider all soups, taking finite soups doesn't ruin norm boundedness. So in CK, now I do things in CK. So in CK, this set is still norm bounded and it's still equicontinuous. But this means that we can use Arcella-Ascoli again.
I have a feeling that.
So it's relatively compact. In CK. But now the inclusion, when we have this IE, when we identify IE with CK, so it means that A check is relatively compact in IE with this E norm. So hence it's relatively compact in IE, but now the inclusion of IE into X is continuous. So this means that this set is relatively compact in X. And well, once we know that it's relatively compact, then it must have a convergent subsequence. Subnet. It's a net, so it has a convergent subnet. But because the whole net is monotone, the whole net is increasing. If you have an increasing net with a convergent subnet, then the whole net is convergent. So this is really the end of the proof. So even though the statement itself is purely a Banach lattice statement, but the proof goes through Arcella-Ascoli theorem, so I think it's a nice proof. Okay, I think I will probably stop here.
Thank you very much. Questions, please.
Sorry, I had a question concerning Archimedean. In the beginning of your talk, you said all should be Archimedean.
Yes.
But, is it all about the presence of unit element, right? Unit factor?
No. Archimedean just means that if you have two elements in the positive cone, such that for every natural number, okay, so given if for every natural number n x is less than or equal than y, then x is 0. Intuitively, it means that there are no infinitesimals.
I see. Okay. Yeah,
so a counterexample would be lexicographic order. Lexicographic order is not Archimedean. And every Banach lattice is automatically Archimedean. So if you're only interested in Banach lattices, then this condition is for free.
Okay,
it's a very weak condition. It is it follows from pretty much every other reasonable assumption.
Okay. Okay. And one more question concerning your A in your previous proof, A hat. But you said it should be it can stay out of Y.
Right, because Y is just a subspace. It's not a sublattice. So when we take supremo of elements, like if we have, so here, if we have X and Y in A, so then X and Y are in Y, but the supremum of X and Y need not be in Y, because Y is just a subspace.
I see. But at the same time, it's going to be inside of C of K. Am I right?
Yes, because C of K is a lattice and IE is a lattice.
You have an isometric embedding. Okay.
Yes, so
okay.
we put, so IE sits inside of IE, but this is a sublattice.
Okay.
So in IE, we safely can consider, so
Okay,
this
yes,
check
yeah.
will definitely be contained in IE. It may not be in Y, but it will be in IE.
Okay, yeah, I got it. Thanks. Okay. Mhm.
More questions, please. Well, I have a question about properties of the injective tensor product that you've just constructed. Maybe the question is rather naive. Is it commutative and associative,
Well,
like the Banach space
yes.
injective tensor
Well,
product?
okay, it's definitely commutative in the sense that this is isometrically isomorphic to Y. You can prove this directly, or you can deduce it from this fact that the tensor norm, this norm, the lattice injective norm, can be reduced to the usual injective norm, and the usual injective norm is symmetric. This is one way. Another way is to do it directly from the definition. It's possible to do it directly from the definition. For associativity, I haven't checked it, but somehow I thought that it should be associative. I would be very surprised if it's not. It's a good question. I didn't even think of for checking this, but you are right. I should check this.
Oh, thank you.
Okay.
Are there any other questions?
So maybe as a follow-up to the previous question, so do you know what about the Fremlin projective tensor product? Do we know that it's associative? I mean,
Well,
it should be, right?
I always presumed that it was, but I actually, as now this question comes up, I never verified it. I should sit down and verify it.
I mean, this is probably true because of this extension property.
Just from the universal property, I mean.
Yeah, probably, yeah.
Yes. It should be true, but I never actually wrote it down carefully.
Okay, if there are no more questions, we thank the speaker again. Thank you. Большое спасибо. Очень интересно.
Спасибо. Спасибо.
Аристополи.
Спасибо.
Ну тогда до встречи через неделю.
Да.
See you next week.
Желаем всем прожить эту неделю весело.
Спасибо.
Спасибо.